Okay, thanks everybody for coming back. My name's Kerry, and I'm going to talk about electromagnetic imaging of subduction zones. And I'm really happy to be giving this presentation after Christy's really good talk on magnetism and melting, because one of the key uses of EM methods in a subduction zone setting are to image melts and free fluids coming off the slab. And so I'll talk quite a bit about that. So it was nice to have, now that you've seen Christy's lecture, some of the things when I show solid eye and things like that, it'll be a little bit easier to digest. Also want to acknowledge Sammer, who's over there, who contributed some slides to this, as well as Stephen Constable. So this being sort of a tutorial lecture, I broadly divided up the talk into 3 different pieces. Sort of the why do we care, why should you care about electromagnetic methods, and that's because they measure electrical resistivity, which is a physical property of geologic materials. Then I'm going to talk about the actual geophysical methods that we use to measure electrical resistivity in the Earth. And then I'm going to give a whole suite of subduction zone imaging examples that will go from looking at the shallow crust at the trench, looking at the forearc, and then looking at sort of crustal and arc magmatism settings. Okay, so what are electromagnetic methods? Well, they're methods that measure time-varying electromagnetic fields in the Earth. So they're not static methods like DC resistivity. They're actually time-varying electromagnetic fields. And we measure the response of the Earth to those time-varying electromagnetic fields. In the same way that, like, if you go out and do a seismic experiment, you're measuring the seismic response of the Earth to whatever the seismic source is, whether it's an earthquake or an air gun. So it works like this. We have sources and then receivers, and generally the more sources you have and the more receivers you have, the more resolution you have. There's several different types of sources that we can use for EM methods. The easiest one is a natural source field. They're just ambient plane wave electromagnetic fields associated with something called the magnetotelluric method. And these are low frequency electromagnetic fields that are generated in Earth's ionosphere, and they diffuse down into the Earth and induce secondary electric and magnetic fields. And we can do this for low frequency deep soundings in the crust and the mantle. If we want to image shallower structure and in higher resolution, then we need to create our own artificial sources. And the 2 primary source types that you can use are a grounded wire, where you inject a current into the ground or into the ocean, or you can use a loop source like this, where you have a loop of wire and you pulse a current through that, and that generates an electromagnetic field that diffuses out from that source. Primarily for the subduction zone imaging, where we're trying to image things on the scales of kilometers to tens or hundreds of kilometers deep, we're going to look at the MT method and then these grounded wire sources. These loop sources tend to be really good for shallow imaging in the upper 100 meters or so, and in fact there's been a lot of use of these loop sources and receivers for airborne electromagnetics, and some of you may be familiar with like helicopter EM surveys that are really high resolution, but unfortunately they don't sense deep enough for us to use for subduction zone imaging, unless you were trying to image, say, shallow magma on an arc volcano. And then the receivers that we use are very similar. We can have either a grounded wire, which would measure the electric field, or we can have an induction coil, which is a very sensitive magnetometer. It measures the time-varying part of the magnetic field, so it's completely insensitive to the static magnetic field. And so that's sort of an overview of what the geophysical approach looks like. Now I'm going to talk about resistivity and why you should care about measuring it. So electrical resistivity, we tend to denote it with the Greek symbol rho. It's an intrinsic property of a material. The units are ohm meters. Sometimes we'll write it as omega meters. And it's simply, you can determine resistivity of a sample simply by putting it in a series circuit and measuring its resistance. So you could use an ohm meter, although in practice we use much fancier approaches than that. You measure the resistance of the sample, and then you simply scale it by the area, the cross-sectional area, and the length, and that gives you the resistivity. So if this is resistivity, it's just like density or seismic velocity. There's an intrinsic value. Every material has an intrinsic resistivity. And then conversely, if you actually wanted to know the resistance of a sample, you could take its resistivity and then multiply it by the length, divide by the area, and that would give you the resistance of a sample. Okay, and then, so in electromagnetics, we tend to flip back and forth between talking about resistivity and talking about conductivity, and they're basically the same thing. One is the inverse of the other. So 1 over rho is the conductivity, and we tend to write conductivity as the symbol sigma. And you'll see me switch back and forth between those. So resistivity has units ohm meters, and conductivity has units of Siemens per meter. So this is a chart to sort of impress you with the huge dynamic range of resistivities that we could expect to see in the Earth for a whole range of properties. Here we're spanning about 19 orders of magnitude, although in practice what we tend to see in our experiments is only about 3 or 4 orders of magnitude. But there's a whole variety of different materials here. Let's see, what can I draw your attention to first? So like basalts, lavas, and igneous rocks, these tend to be fairly resistive. So this is a logarithmic scale here as well. So this would be 1,000 ohm meters here. Something like partial melt, so all the stuff that Christy was talking about in her talk, those tend to be fairly conductive. So there's usually about a factor of 1,000 contrast or more between a pure partial melt and then a solid igneous rock or basalt. And then all these things have quite a range of conductivities. Like any given material has quite a range of conductivity that it can be, and this depends both on temperature as well as the porosity and fluid content. So for example, a sandstone here, if it's very dry, can have a very high resistivity, over 1 million or so. Whereas if you fill the pores of that sandstone, say it's like a 20% or 30% porosity sandstone, its resistivity is going to be closer to 1. So it's very sensitive. EM methods measuring resistivity were very sensitive to the porosity and fluid contents of rocks, whether they're filled with seawater, which tends to be conductive, or melt. And then some sort of end members here. Air is very resistive, about 10 to the 13 or so. And then like graphite and some ore grade minerals will be very, very conductive. So here we have 10 to the minus 5. And if you were to look at the types of metals that are used in wires like copper, gold, and silver, those are actually a few orders of magnitude over to the left here. They're very conductive. So resistivity spans many orders of magnitude. Yeah, Sean?
What's the pressure here?
This is just sort of at ambient pressure. I'll talk about that in a second here. Ends up the pressure dependence of most of these rocks and minerals. The pressure dependence of conductivity is fairly low. It's very weak, especially compared to the effect of porosity and fluid content and temperature. Those are much bigger effects. But sort of the primary variable that affects the bulk conductivity of rock is its porosity and fluid content, and then the secondary effect would be temperature. Let's see here. Okay, so another thing, a lot of EM methods have been, the technology has been advanced a lot in the last decade or two due to a significant amount of investment from the oil and gas industry. And they were interested in this resistivity contrast here, where oil or gas in the seafloor tends to be fairly resistive, maybe 100 to 1,000 ohm meters. And an oil reservoir on the continental shelf will be resistive, and it'll sit in these conductive wet sandstones. And so there's this nice resistivity contrast. And in the early days, the late 1990s, early 2000s, when this technology was being commercialized, there were people in the oil and gas industry that were saying that you could use resistivity as a direct hydrocarbon indicator. And we were like, no, no, no. If you go out and you measure something and it's 100 ohm meters or 1,000 ohm meters, it could be anything on here, as well as all the other things that aren't shown on here. So, for example, you could see a resistor, and then if you work in an oil company, you could say, I want to go drill that, and your company will spend $40 million drilling a deep water well, and then maybe if you didn't know what the geology was, maybe the resistor was a basalt, a sill, or maybe it was like a limestone or carbonate or an evaporite deposit. So, resistivity is not a unique indicator of rock type. We need to integrate with geology and other geochemistry and other methods in order to build up an understanding of what the resistivity is telling us. Okay, so that was resistivity of rocks and minerals. There are models for if we have 2-phase or 3-phase systems to predict what the bulk conductivity would be. And so we can use various mixing laws. The Hash and Strickman bounds are nice because there's seismic equivalents to these. And they're basically theoretical bounds for a 2-phase system where you have a solid conductivity and a fluid conductivity and then a porosity beta in that. And then there's various degrees of percentage of the fluid phase, where if this is 0, beta is 0, there's no fluid. If beta is 1, then it's 100% fluid. And so the lower bound corresponds to basically that fluid being isolated in spheres, and the spheres are not very well connected, and so you don't get an enhancement of conductivity because simply the conductors are isolated. Whereas the upper bound, you can think of that as like a network of like wires or grain boundary conductors that basically, if the yellow is the solid matrix and it's resistive and the gray is the fluid's acting like little wires that are short-circuiting the bulk conductivity. We also have Archie's law, which works well for fluid-filled sediments as well as fractured igneous rocks. And Archie's law in this simple form here is basically says the bulk conductivity you measure is equal to the fluid conductivity times the porosity to some exponent m. And this was empirically determined about 80 years ago or so by Archie from looking at well logs that the oil and gas industry had collected. And basically this exponent here tends to be around 1.3 to 2. There's various studies that try to pinpoint what a good exponent is for different types of rocks and materials. But Archie's law, conceptually, you can think of this as like this sort of matrix of variable grain sizes, and it's predicting what the bulk conductivity for that would be. Whoops. Okay, so this is an example chart showing you the Hashon-Strickman bounds and Archie's law. For the Hashon-Strickman bounds, I used the solid matrix had a resistivity of 1,000, and then the fluid had a resistivity of 1 on here. And so the Hashon-Strickman lower bound is showing that basically you don't get a drop in resistivity or an enhancement of conductivity until the fluid fraction reaches about 10% or so. So if you have fluid that's not well connected, you're going to need a lot of it before the resistivity drops. Whereas if you have a fluid that's very well connected and can be described by the Hashon-Strickman upper bound, then you'll have this really nice drop in resistivity or increase in conductivity, even for very low melt fractions. So for example, if this was, you say, a basalt or a peridotite, and this was melt, then even a small amount of melt is going to give you this nice enhancement in the resistivity. And so this is one of the primary reasons why EM techniques are good for mapping melt. And if you remember from Uli Fall's talk on Monday, he showed those images where you could see the melts coating the grain boundaries. And so they're very well, the melts tend to be, even low degree melts tend to be fairly well connected. And so this Hashon-Strickman upper bound is a good approximation to their bulk conductivity. And then also I'm just showing here the Archie's law, and this would be applicable for sediments, not for this system here, but you can basically see that there's this nice decrease in resistivity as the porosity increases. Resistivity also depends on temperature, and so this was something that you also saw in Uli's talk when he was talking about seismic velocities, where you have, at least for silicate minerals at mantle temperatures, you have this nice exponential relationship here where there's this thermally activated conductivity, where you've got Boltzmann's constant in the temperature and then this activation energy here. And so this is just an example showing some dry olivine conductivity models that were derived from various laboratory data here. And so we've got one on temperature plotted here, and then this is the log of resistivity or conductivity here. And where this exponential relationship is valid is down here at these sort of lower temperatures. And then there's other things going on up here that give this curvature. But basically you can see that over sort of temperatures that we'd expect in maybe the lower crust down into the upper mantle, there's quite a bit of range, maybe an order of magnitude or two variation in olivine conductivity. So EM methods will be sensitive to the thermal structure. They're also sensitive to the water dissolved in olivine, and we've heard about this hydrous olivine in a couple different presentations here at CIDR. Water can be structurally incorporated into olivine through hydrogen defects. And there's been a whole series of laboratory studies that have made measurements of hydrous olivine conductivity over the last decade or two, and it's been a really controversial topic because the various groups have got these results that vary by over an order of magnitude. And that's summarized in this paper by Gardes over here, where they were trying to unify these results that show these huge discrepancies. So here's conductivity here, and then this is concentration of water in parts per million weight, going from really low values of about 3 up to 1,000 or 3,000 or so. And these are the various models derived from different groups. And in the Garday's paper, they tried to unify, and they basically found this model that goes through the middle, which I guess is a good way to unify something with that amount of spread. And then these are these are at 1,200 degrees C, so sort of a mantle temperature. And then, because it's difficult to make measurements at this these high temperatures, a lot of the measurements are actually made at lower temperatures, and then they use those thermal activation models to extrapolate them to higher temperatures. But you can see there's a whole range of values in the conductivity here, depending on the different groups. And so this has not gone unnoticed by people in the EM community that actually collect MT data to try and image the Earth structure. And Samar and some others formed a CITER working group that met last summer to try to make sense of this. And they're slowly starting to chip away at what some of the uncertainties are in these measurements and ways that they can be improved in the future. And one of the uncertainties was basically different methods were used to estimate the water content of these samples. And so some of this variability may simply be that the water content measurements were not as precise as they needed to be. And so the bottom line, though, is that more experimental work is needed. These sorts of models are really important for interpreting the field data. And so if we don't have good models for interpreting the field data, then we can't make really robust conclusions about what's going on in the Earth. Okay, so another thing that you need to be concerned with sometimes is anisotropy, and that's simply that electrical conductivity can vary as a function of direction, so and that would be the direction that the electric currents are flowing in the Earth. There's two different ways to get anisotropy. You can get a macroscopic anisotropy from layering in the sediments, so if you have alternating resistive and conductive layers, that'll make the parallel conductivity different than the perpendicular conductivity going through the sediments. And bedding planes and fault fabrics can also give you anisotropy. And then I'll show a really nice example of a faulting fabric giving us a crustal anisotropy. And then we can also have macroscopic anisotropy for mineral grain alignment and shearing fabrics. And these are the types of things that you would see, say, in like the asthenosphere or in the deforming mantle of the wedge. Okay, so that's resistivity and like some of the things that affect it and how it can be useful for studying the Earth's properties, especially in a subduction zone setting. Now I'm going to give you a brief overview of EM geophysics to try and sort of demystify what EM geophysics is. Because unlike geodesy, where you can sort of imagine plates deforming, and you can actually slide little plate models around, imagine that, or seismology, where you can imagine, or maybe you felt an earthquake, but at least you can visualize the ground shaking. It's really hard to envision what actually an electromagnetic geophysical sounding is. And in fact, if you've ever felt an electromagnetic wave, it's probably the last thing that you're feeling because you're being electrocuted, So, so I'm going to go through a little bit of the math and then show you some animations of the fields and things like that. And hopefully this will demystify EM for you and you'll feel like you have at least a budding intuition on how it works. So, this is also, I want to qualify and say, we're looking at the low frequency form of Maxwell's equation, so at about 1 kilohertz and lower frequency. If we're at higher frequencies, there'd be additional terms in some of these equations that have been neglected. So the most important equation for EM physics is Faraday's law of induction, which some of you may be familiar with. And that simply says that if you have a time-varying magnetic field here, so this is dB dt, where this is one of the magnetic field quantities, that if you have a time-varying magnetic field, you'll generate this electric field. And if you're not familiar with vector calculus, this is called the curl operator, and it simply corresponds to basically it says that basically this electric field is solenoidal. It wraps around a line of current or line of the magnetic field. And one way to you may be familiar with this is simply if you have a magnet and you move it through a coil of wires, you'll induce a voltage or an electric field on those wires. And that's simply what Faraday's law is saying, is if you have a moving magnetic field, you'll generate an electric field from that. So that's one important quantity. The other important equation that we have is Ampere's law. And Ampere's law basically says that if you have some current flowing in the earth or in a wire, you'll generate this solenoidal magnetic field that wraps around that wire. And so again, we've got that curl operator here, but it's now applying to the H magnetic field rather than the electric field. And we can have a current here, J, which is just simply some current flowing in the ground, and then there's an additional term here, JS, which is any imposed source. And so like in our controlled source EM applications, JS would simply be the dipole transmitter or the loop transmitter. And so these are equations that describe how electromagnetic fields behave in the Earth, but they don't include the material properties of the Earth. And so we can introduce the material properties of the Earth through what are known as the constitutive relations. And so we have this magnetic field B here is known as the magnetic flux density, and it's equal to the magnetic field times mu, which is the magnetic permeability. And the magnetic permeability it varies very small in general for most Earth materials. Like it's about a part per thousand or so. And so we can generally neglect that in EM geophysics. At least we don't have to worry about its variations. Whereas we have the other constitutive relation, which is between the current and the electric field. And that's where the conductivity comes into play here. And we know that this varies by orders of magnitude. So this is a part per thousand or so, and this is orders of magnitude. So conductivity is more important in these equations. So those are the two equations. They're coupled, right, because they both have electric and magnetic fields in them. And so we can insert this term for the current density into this equation. We can take its time derivative and then substitute it in for B in this equation and insert one in the other. And you arrive at what's called the governing electric field equation for EM geophysics. And this is for any sort of model, whether it's 1D, 2D, or 3D, this is the governing equation. And this is, just to break it down really quickly, if you're not familiar with these sorts of equations, this is a second order derivative. Because the electric field's a vector field, we have these special curl operators, but you just think of this as a second order derivative. There's a first order time derivative here. And so we've got the second order spatial derivative plus these coefficients times the first order time derivative, and then we have our forcing function or source function over on the right. So this is basically just a diffusion equation. So EM induction is basically a diffusive process. It's kind of like how heat flow in the Earth is a diffusive process. And so what that means in terms of the resolution is that it's not a wave equation method like seismology, or in particular full waveform seismology. So we don't have as high a resolution as you would get from a full waveform seismic method, but the resolution is much better than gravity and magnetics or DC resistivity, because those methods are governed by Poisson's equation, where you would have no time derivative here. That would just be equal to 0. And so having this first order time derivative helps with the resolution of EM methods. And okay, so just a little bit more math here to help develop your intuition. So if we take that equation and we just assume that the electromagnetic field is a plane wave, that's sort of the simplest case, and it's just a plane wave traveling vertically down into the Earth, the solution looks like this. And it's simply saying that the electric field is a function of depth and time, has four terms here. The first term is basically whatever the amplitude is at the surface. The second term is this complex exponential. This is just saying it has sinusoidal time dependence. The third term is another complex exponential as a function of depth. That just says it has sinusoidal depth dependence. And then there's this last exponential decay term here, which is a real term. And it has, it's just saying that the field decays exponentially with depth. And this alpha is where the conductivity and then the angular frequency omega of the plane wave comes into play here. So one other really important concept for understanding EM is something known as the skin depth, ZS. And that's simply the depth Z, where Z is equal to 1 over alpha. And so this amplitude decay will equal to 1 over E, or basically saying that the field decays to 37% of its initial value. And if you just go through and plug this in and then expand these variables out, basically the skin depth is approximately equal to 500 times the square root of the resistivity times the period of the wave. So for example, if you had a 1 ohm meter, a rock that it was 1 ohm meters resistivity and you were looking at a period of 1 second for the wave, then the skin depth would be 500 meters. Conversely, if you had a rock that was 100 ohm meters, so more resistive, and then you went to much lower frequencies of, say, a period of 100 seconds, then the skin depth would be 50 kilometers. So because the conductivity varies so much in the Earth, and because we can measure things at really low frequencies or really high frequencies, we can get this huge depth, huge range of depth sensitivity through this skin depth quantity. So that's the math. This is what it actually looks like if you plot up that plane wave as a function of depth here. So I generated, I just used that equation with a frequency of 0.1 hertz and then a resistivity of 100 ohm meters. And this is what it looks like as a function of depth here. These little envelopes here are just showing the exponential decay term, and then these are the skin depths here. And we can animate this, and this is what it looks like in time. So there's sinusoidal depth dependence and then sinusoidal time dependence. And so these are what the EM fields look like as they're diffusing into the ground. And generally, we lose sensitivity within a few skin depths. So you can compute the skin depth of the EM wave, and you can use that as a proxy for how deep the methods can be able to sense. And generally, anything that's deeper than 2 or 3 skin depths, we don't have sensitivity to. And then we can use Faraday's law. So this is the electric field as a function of depth. We can use Faraday's law, and for this one-dimensional plane wave, it's simply this. And it basically says that the magnetic field associated with this plane wave is equal to the vertical derivative of this electric field. And then because we know that the vertical dependence of the electric field is proportional to this minus alpha z, and whereas alpha has conductivity in it, we know that the magnetic field is going to be proportional to the conductivity of the ground. And so if the ground is more conductive, then this decay term is faster and you get a bigger magnetic field, whereas if the ground is resistive, alpha is small, and you get a much smaller magnetic field from that. So that's basically the basis of what's known as the magnetotelluric method, which I already mentioned a little bit, where we've got these plane EM waves diffusing down into the ground. It's a low frequency technique. We tend to measure the fields at very low frequencies down to about 1/10 of a millihertz or so. In the ocean, we can measure up to about a 1 hertz or so frequency. On land, you can get much higher frequencies, up to around a kilohertz or so. And so this gives you a huge range of depth sensitivity from the near surface down to the deep crust and mantle. We measure these time-varying horizontal electric and magnetic fields at the surface, and basically the ratio of orthogonal components, so perpendicular components of the electric and magnetic field, are going to be proportional to the ground conductivity. And so let's see here. So how do we actually measure these fields? Well, in order to do it in the ocean, we need a ship, preferably a big ship like this, like the RV Thompson. And so we go out with a bunch of grad students and postdocs and techs and a bunch of instruments. And this is an example from a cruise we had offshore Umnak Island a few years ago, where we had a fleet of about 40 instruments on the back deck of the ship, and the team of grad students and postdocs and techs assembled the instruments. It's basically a data logger, and these big long arms hold electrodes at the end, and so we use the electrodes for measuring the electric fields. And we can we can deploy these things in about 30 minutes or so. It takes about 30 minutes to assemble it and throw it over the side of the ship. And because the ship is, while you can be putting the instrument together while the ship is driving around, it's really efficient to collect or to get these deployed. We can deploy, a fleet of 50 of these things in about 24 hours because you just pop one over the side every half an hour, as long as the stations aren't too far apart. So this is what it looks like when we're deploying it. Keep going forward here. There's another close-up in a second. Okay, so these little blue tubes here are the induction coil magnetometers. So we measure the magnetic field in each direction on here. And then again, the electrodes that we use to measure the electric field at the end of these long arms. The long arms are simply, there's nothing fancy about them. They're just plastic tubes, and then they just hold an electrode at the end, and a wire goes down the middle. We just use these tubes because they're stiff enough so they're not going to flop around too much on the seafloor. And then in order to make these measurements, the magnetometers are really sensitive to tilts and vibrations. So we had to design these big concrete slab anchors that are attached to the instrument frame, and that holds the instrument relatively stable on the seafloor. And then we have these flotation packages here, which are used to float the instrument back up to the surface when the release mechanism, which is shown here, is triggered at the end of the experiment. So let's see, let's keep going on here. Whoops, wait. Okay, yeah. So, okay, so let's go here. Yeah.
Can you explain in a couple of words why the frequency is much smaller, what we can reach in offshore measurements than inland measurements?
Oh yeah, sorry, I forgot to mention that. Yeah, the reason why we can't measure the high frequencies in the ocean is simply because the skin depth of the EM fields in the ocean, at 1 hertz in seawater, the skin depth is about 270 meters or so. So once you're down, say in the deep ocean, say at 4 kilometers depth, you're like, 20 skin depths down. So there's basically no energy at 1 hertz. You have to go down to about 20 seconds or so to get the really high frequency energy. Whereas if you're up on the continental shelves in say a couple hundred meters of water, then you can get that 1 hertz energy and stuff. So it's really, it depends on the depth of the ocean, really. But the ocean's basically a big filter. Okay, so I wanted to show you an example of what the actual fields look like. We had a project a few years ago where we had 51 receivers deployed off the coast of Oregon and Washington as part of this subduction zone imaging project. And so I basically just took the raw time series of the electric and magnetic fields and then created these vector arrows, which shows the induction as a function of time. So this is 5 hours, and it's like sped up really fast here. But basically the red's the electric field and the blue are the magnetic fields. And you can see that they're generally orthogonal to each other, as you would expect from Faraday's law. More formally, the electric and magnetic fields are related through this tensor relationship, where you've got the horizontal electric field and the horizontal magnetic field, and then this tensor here. But this is basically what an MT experiment looks like. These fields that we measure on the seafloor, they're reflecting what's going on in the ionosphere, which is the conductive part of Earth's atmosphere. That's about 90 kilometers above us. And so there's various currents that flow around in the ionosphere. They're formed by the solar wind hitting the Earth, and then it sets up these charged currents in the conductive part of the atmosphere. And so as those currents vary, it sends these plane waves that diffuse down into the Earth. So there's like MT fields going through this room and you right now. They're just really small and you can't feel them. There's no ridiculous question, yeah.
So seismologists like big earthquakes.
Yeah.
So do you like big solar storms?
Yes and no. Yeah, I mean it's a good question. Yeah, we like big activity. I mean that certainly helps, especially when we want to measure the short period or high frequency fields on the seafloor. If there's a storm, if there's not a storm, maybe we only get data to 10 seconds period. But if there's a storm, maybe we'll get data all the way up to 1 second or 1 hertz. But storms can sometimes be bad because we rely on the assumption that the field is a plane wave. And so if you have like a localized storm that causes like a very isolated current system up in the ionosphere, that can lead to spatial gradients in the source field and other complications. So storms can sometimes be good, sometimes they can be bad. I can tell you more about that, but I'll go on and anyway, so that was marine MT. Land MT, it's the same sort of thing where you measure electric fields and magnetic fields, but you have to do a lot of digging, so it's a lot harder and slower. This is just a picture from a project that we had in Umnak Island to look at magmas beneath Akmak volcano. So we've got induction coils. On land, because these things are very sensitive to vibration and wind, we have to dig little trenches that are about 1 foot deep or so and bury them. And when you're out and like inside a caldera volcano like this and you've got this wet tephra, it's actually pretty easy to dig in. But if you go out to some place like the San Andreas Fault where it's dry and rocky, it takes a lot longer to install these. But on average, you can deploy a station in about an hour or two. And for the electric fields, we basically have big, long wires, which you can't see in this picture, but they're wires that go out 50 meters in each direction. And we have an electrode in the north quadrant, the south, and the east, and the west. And we use that to measure the electric fields. Let's see here. Okay, and so, yeah.
Can you put them anywhere you can dig a hole? Or is
Pretty much,
there a
yeah. I mean,
limitation?
anywhere you can dig a hole, and sometimes people put them anywhere you can't dig a hole. Like, there's a project that's supposed to be going on right now in Yellowstone where they didn't get permission to dig holes. So they're actually just laying the magnetometers on the ground, and they're putting little tents around them and putting sandbags on them to try to keep them from vibrating. So that's because they didn't have permission to dig. So yeah, so pretty much anywhere you can put a sensor on the ground, you can make a measurement. Ideally, if you put it in the ground, you get a lower noise measurement. The electrodes are one of the complicating factors. If you work on like bare rock or ice or something where the ground is very, very resistive, then you have to use these special capacitive electrodes things. So there are some subtleties in the equipment depending on where you go, but in general, anywhere you can go, you can make a measurement. Some people are even trying to make airborne measurements at high frequencies.
So, Kerry, I have a question also.
Yeah.
I've often wondered why it's such a pain to deal with these 50-meter long lines.
Yeah.
Why can you do such short electrodes in the oceans, but on land we always do these big long lines?
Yeah, it's the signal to noise ratio. It's a lot quieter in the ocean. Like we don't have any cultural noise. There's no wind noise. I mean, sometimes we'll get water current noise, and we've seen that before. If you have a bottom current, it'll shake the instruments. But in general, it's a much quieter environment. It's also more conductive. The seawater is around 0.3 ohmmeters, and so it's real easy to make a low noise electrode and a low noise amplifier for that conductive environment. On land, the impedances of these systems are really high, so that you're not actually drawing current from the ground, and that basically just makes it an inherently noisier measurement. So you get around that by using longer dipoles. Because the electric field that we measure, it's a volt per meter. So every meter longer that your dipole is, that means you get a bigger voltage. And so, we generally go with these plus and minus 50 meter dipoles. Some people have experimented trying to do like 20 meter dipoles and things like that, but it just means that you have that much more noise in your measurement. So, but yeah, it'd be great. I mean, if you wanted to do MT on like another planet or something, then you'd want to have like a 1 meter dipole that was suitable for a lander or a rover. So it's definitely something that people are thinking about. Okay, so the workflow for MT looks something like this. We go out and we collect time series, and so this is an example. I think this is like 30 minutes of signal from somewhere in the world, where we've got the X and Y magnetic fields, and you can think of this as like north and east magnetic fields, and then the north and east electric fields here. And you can see that the orthogonal components are correlated, so X and Y are correlated. Or BX and EY are correlated, and then BY and EX are correlated as well. And so we'll make lots of measurements. The time series, depending on the frequency bandwidth you're interested in, you can have the sensors in the ground for hours, or days, or weeks, or months. For most of the things I'm going to show, the sensors, we're making recordings for days to weeks. And then we take that time series and we do a lot of data processing, which means convert it into the frequency domain and then estimate that response function, the tensor response function. And we do that using a robust array processing method. And then we get the MT responses, which are basically an amplitude and phase. I'm not going to go into the detail of these, but it's basically this is the time series. And from an MT person's point of view, this is what we'd call the data, because this is what we're actually going to model are the responses. And so then we take the collection of those responses from a bunch of stations, ideally tens or hundreds of stations, and combine them and run them through a nonlinear inversion to solve for a conductivity model that can match all of the responses. And there's a whole, like you could give a whole day lecture on different inversion techniques and stuff. And it's sort of the state of the art for MT inversions now are these sort of regularized gradient-based inversions in 2D and 3D. Okay, so let's see, let's go on. Now that was the MT method. That's good for crustal and mantle imaging. If we want to get really high resolution imaging of the shallow crust or at least the oceanic crust, we can use the controlled source EM method. And that's where we simply introduce this dipole transmitter into the ocean, and we transmit fields in this 0.1 hertz to 10 hertz band. So this is how we get the high frequency response in the ocean. We use this artificial source. And we tow the source close to the seabed because we know the energy is going to dissipate or attenuate really rapidly in the ocean. So we tow this as close to the seabed as we can. Depending on how rough the seabed is, that means either 20 meters above the seabed if it's flat, or if it's really rocky, it might be 100 or 200 meters above the seabed. The closer to the seabed, the better coupling you get. And then we measure the way that the EM field from this transmitter diffuses out through the seawater, the air, and through the geology by measuring, by putting out an array of receivers. And so we simply want to measure how the transmitted field gets attenuated by the Earth, and that tells us that's going to be proportional to the conductivity or sensitive to the conductivity. So it's the same receivers that we use for MT. So basically we can go out and deploy the receivers. They'll collect MT data at the low frequencies, and while they're doing that, we can tow the transmitter by, and they'll collect CSEM data. So it's nice. You get sort of 2 data sets for the price of 1. Good for imaging to a few kilometers depth. And this technology has been around for doing these deep ocean controlled source EM soundings. It's been around since the late 1970s. It was developed in academia for measuring the conductivity of the lithosphere. And it was around the late 1990s that Statoil and ExxonMobil figured out that you could map oil and gas reservoirs with this technique. And so they heavily invested, and a bunch of oil companies heavily invested in the technology. And so it's seen a huge improvement in capabilities, both in terms of the modeling codes that we now have and the instrumentation and data processing techniques. And that's largely due to this huge investment by the oil and gas industry. So I want to show you just a really quick example that's from an oil and gas study, but it helps show you why the CSEM method is so useful. And so we've got this model here where the ocean's conductive, and we've got conductive sediments, and then there's this resistive thin layer, which is simulating sort of a infinite oil and gas reservoir. And so I ran this through my 1D modeling code, where I've just put a dipole right at the seabed, and this movie that I'm going to show you is going to show you the instantaneous direction of the electric field through these arrows, and then the colors show you the amplitude of the field. And this is on a logarithmic scale, so, spanning several orders of magnitude. But basically, this is the ocean here, these are the sediments, and this is that thin resistive layer that's simulating an oil and gas field. And so the key thing to note with this simulation is that in resistors, the electric fields decay slowly, and they have a high phase velocity. And in conductors, they decay rapidly, and they have a slow phase velocity. So what happens is when we pulse the transmitter, you get good coupling into this resistive layer, and because it's resistive, the fields decay slowly, and they have a high phase velocity. So it acts like a waveguide, and you can get this EM wave transmitting out through this thin layer. You can actually see with this little phase front that comes through here, you can actually see it traveling up from the resistive layer and down from here. And whereas the energy that goes to the ocean is traveling really slowly, and it's attenuating very rapidly. So if you're an oil and gas company and you have a bunch of EM receivers on the seafloor here, the presence of this thin resistive layer is going to give a much stronger amplitude and higher phase velocity signal than if there was no resistive layer here. And that's really why the oil and gas companies are interested in this technology, because if you've got a reservoir, you'll get a stronger electric field than if you don't have a reservoir. So that's sort of a simplified look at how the CSEM method works. For a real survey, we tow the transmitter along. We've got tons of receivers out, and so you get all these different geometries. And one other thing that I forgot to mention, the CSEM method, in addition to having this compact source here that we can tow around, it actually gives you a much higher resolution image than you can get with MT, simply because the source field, it's not a plane wave, it's not just horizontally polarized. The source field actually rotates around, and so we have both horizontal and vertical currents, and so that gives us a much stronger sensitivity to the conductivity contrast in the subsurface.
Kerry?
Yeah.
Quick question.
Sure.
So are these inversions nonlinear, or?
Yeah, they're all nonlinear inversions. Yeah, the forward operator depends on the conductivity and stuff. So basically we use basically it's like a regularized Gauss-Newton approach to solve it. That tends to be the most robust. At least we do that for sort of the low parameter inversions. For high, if you have like a 3D inversion, then you have to go to something like a nonlinear conjugate gradient approach.
Okay, thanks.
Yeah. Okay, so to collect the controlled source EM data, we use the same receivers like I showed in the previous movie, and then we have a transmitter. The transmitter that we developed at Scripps is known as SUSY, the Scripps Undersea EM Source Instrument. Basically takes a high voltage signal that you put on the deep tow cable here, and then inside this pressure case is a really large transformer. It's about this big, and so that transforms the high voltage into a high current signal. And then we have some switching circuitry, which basically generates the waveform that we want to transmit across the electrodes. And then we have an antenna here where there's two cables going out to an electrode. One electrode is close to the transmitter, and then the other electrode is actually 300 meters away. So we've got this 300 meter long antenna that we're towing right above the seabed. And then there's a bunch of other sensors on here, like we've got, it's really important to know the position of the transmitter because the fields decay so rapidly with distance. We need to precisely know where the transmitter is. And so we've got an acoustic unit on here which we use to triangulate the transmitter. There's a pressure gauge, there's a downward looking altimeter. But the altimeter is really important because you don't want to crash into the seafloor. So it's almost happened a few times. And so this transmitter that we built at Scripps can generate up to about 500 amps. The latest, greatest transmitters that they're using in industry transmit about 7,000 amps. So they have much bigger cables and things like that and more money. but this is what it looks like. So we can tow this thing. It's both the receivers and the transmitter are designed to be deployed up to 6 kilometers water depth. So we can go to a lot of places in the ocean, not the deepest deep ocean trenches, but most of the ocean we can cover with this system. So the CSEM workflow, we basically go out and collect time series. We have the, we actually record the transmitter current. We need to know what we're actually injecting into the seabed. And then you have the measured voltage from the receiver. And so we basically, the processing for that involves converting this into the frequency domain, converting this into the frequency domain, and then removing the source signature of the transmitter. And that gives us the amplitude and phase at the receiver at a series of basically the fundamental harmonics of the transmitter here. And so this is an example from some data from offshore Nicaragua where we've got 0.25 hertz, 0.75 hertz, and 1.75 hertz shown as red, blue, and green. And you can see the fields decay very rapidly with distance. This is position or distance between the transmitter and the receiver. And so this is decay over about 3 orders of magnitude. And so the more conductive the ground is, the faster the decay is. The more resistive it is, the slower the decay of the fields will be. So we measure these CSEM responses at a bunch of receivers, and as the transmitter is towing by, and then we put them all together into a nonlinear inversion, and we solve for the conductivity. And so this is an example that I'll talk about a little bit later on in today's. Well, in fact, right now I'll talk about it. So let's just go on. Okay, so I'm going to go transition into probably the best example of marine EM imaging of the shallow part of a subduction zone. In fact, it's the only real example of using CSEM to image shallow structure at a subduction zone. This was a survey that we did about 7 years ago at the Middle America Trench, where the Cocos Plate is subducting down beneath Central America. And this is the location of the survey region. And the reason why we went to this location for the survey was because of these bending faults that were imaged by seismic reflection data. And I think you've seen this in a couple talks already, where this is the incoming plate here, and this is the trench. And the seismic reflection images shows these really deep, dense bands of normal faults cutting all the way through the crust. So this is the moho right here. These little white dots are where they pick the moho. So this is the oceanic crust. This is the upper mantle. And these faults are so deep, they're going into the mantle about 20 kilometers or so. And so in this paper by Renero et al., they speculated that these would provide permeable pathways to allow seawater to percolate down all the way through the crust and into the mantle, where it would hydrate the peridotite and form serpentinites. So this would be a way to carry down a lot of water into a subduction zone. Some of the corollary pieces of evidence here that go along with this are that if you look at heat flow along the trench here, we are going down the outer rise into the trench. The heat flow seems to decrease with distance to the trench, which seems to imply that there's a lot of hydrothermal circulation cooling the crust. And then the density of, this is also an actively faulting system, which is shown in this plot here, where the number of faults increases with distance to the trench, as well as the throw on the faults also increases with distance to the trench. So this is a very actively deforming system. So the hypothesis was that water was going down on these faults, and so we designed an EM experiment to try and map the water in those faults, and this is what our experiment looked like. We put out this array of receivers in this linear profile crossing the trench here, where the white dots are showing the receivers, and then we towed the EM transmitter along a profile crossing the trench like this, as well as in these two circles, which were designed to measure anisotropy. And this is the first and the only time CSEM has been applied at a subduction zone. It's been used a lot in industry to map continental shelf sediments, but it's never been used in a subduction zone before. So, oh, I forgot to tell you something. So the way that we designed this experiment was that we were really interested in the bending faults here and what was going on. We were also interested in the structure of the forearc. And one of the lessons that my PhD advisor taught me when I was a student was that if you're interested in a target, and in this case it was the bending faults here, you don't want to just collect data over that target, because you won't know how interested it is if you don't have data off target to show you like what the boring part of the model is. So we were primarily interested in this, but we extended the profile all the way off here out into the abyssal plane so that we would have sort of a reference model for what the conductivity looked like before the bending fault fabric formed in the seafloor. And so, so this is supposed to be the boring part of the model, and this is supposed to be the interesting part of the model. And so we went out and collected the data. And Samer was my student back then, and he was looking for a project to work on. And so I gave him the MT data, thinking that it wouldn't, it'd be a good first project, but it probably wouldn't be that interesting. And he ended up modeling and discovering this really interesting feature underneath the boring part of the so-called boring part of the survey. So this is just a little lesson to, don't predict the answer that you're going to get ahead of time, and try to keep an open mind. So Samer found this model where, this is from the MT data, so it's looking at the lithosphere and the asthenosphere, and so basically the upper mantle part of the section here, where we see this really thin conductive feature. It's around 5 to 10 ohmmeters or so and it's at 50 kilometers depth, and it's beneath the resistive oceanic lithosphere. We also were able to model the anisotropy with this code and see that it was an anisotropic feature where it was more conductive in this left-right direction than into and out of the plane of the model. So that was really interesting. And so there's two sort of explanations that we could look at for this conductive feature. One is that it's partial melt. The other is that it could be hydrated olivine. And so for the paper, Samer created this nice plot where we've got resistivity here, and then we're looking at basically water content or melt fraction using different laboratory-based models for each. So this is our observed resistivity here, shown with these gray bands. And then these three curves here are showing predicted resistivity for hydrated olivine with different water contents here, and then 3 different temperatures here. So we're not, precisely certain just how hot the mantle is here, and so we wanted to look at temperature effects as well. And you can see that, regardless of the temperature, we need to have really high water concentrations in order to explain these conductivities. And if you remember from Christie's talk, where she showed the hydrated peridotite solidi, basically these amounts of water would trigger melting at these temperatures here. So basically, yes, you could have hydrated olivine here, but in order to explain our conductivity, there's so much water that you'd have to trigger melting. So that led us to basically take a more conservative approach and assume that our model could probably be explained by melt rather than this hydrated conductive olivine. And so if we assume that there's melt, and we only need a small amount of melt, less than 4% or so, these are what the predicted model conductivities are for different amounts of different temperatures, as well as different amounts of water in the melt. So Christy talked about how water can partition the melt and affect its composition. Well, water, when it gets partitioned in the melt, also affects its conductivity, and that's something that we need to model. And so these are just showing these curves. So depending on whether you think that it's a drier melt or a wetter melt, you get different melt fractions estimated from our model. But the basic conclusion was that this conductive layer was representative probably of a sheared melt layer right at the base of the lithosphere. And we showed that these are also, melt is also thermodynamically stable. It's thermodynamically stable at this age of a plate and at these depths. And so this is showing depth here, or pressure, and these dashed lines are thermal models based on a plate cooling model, where we looked at 2 different mantle potential temperatures, either 1350 C or 1420 C. And then we've got 3 different solidi here. One is the dry peridotite solidus, and then we have a 275 parts per million water, or 505 parts per million water. And so, for example, if we assume the mantle's hotter, 1420, and that it's dry, well, you can see a hotter dry mantle, the geotherm crosses the solidus right about here. So if the mantle's hot, we don't even need water to explain generating a little bit of melt at the depths that we see it in the conductivity model. Conversely, if there is a small amount of water, say 275 parts per million, then we can also trigger melting with a cooler mantle, say this 1315 degrees C mantle. So basically, we showed that it was consistent to, the melt interpretation was consistent with the thermal properties. So that was a really interesting first result. Now I'm going to jump over and talk about the CSEM data for quite a few slides. So most of the EM data that we collect, it's really hard to actually look at those EM responses and say anything about the Earth. You really need to collect the data, get the responses, and then put them in an inversion, and then you can say something about the Earth. This is the one exception to that, where we collected these anisotropy circles, where we towed the transmitter in a circle around some special receivers located in the middle. And these were special, highly sensitive receivers, so that we could measure the really low amplitude fields. These are 60 kilometer diameter circles. And so over on the right here are plots of the amplitude of the electric field as a function of azimuth to the transmitter. So this is when the transmitter's, up here, and then, these symbols are when the transmitter's down here. And so it's just plotting the amplitude. And these are the amplitudes at 0.75 hertz and 3.25 hertz for the abyssal plane circle, and then the bending fault trench outer rise circle is shown here in red. And so the key thing to this is basically if conductivity doesn't vary as a function of direction, these amplitudes should be circular. And that's pretty much what we see in the abyssal plane data. It's mostly circular here. There's not a lot of structure in this, and that's pretty much what we expected to see. Whereas where you have the bending faults over here on the trench outer rise, we get these nice oval-like shapes in the data for both frequencies here. In fact, it's even more enhanced in the high-frequency data. And this is consistent with anisotropy, an anisotropic conductivity in these bending faults. And so we were able to model this with a modeling code by putting in a 5-to-1 anisotropy that's consistent with the bending faults being vertical planes of high conductivity. And so basically high conductivity planes aligned in this direction. And that black line is showing the EM response of that model. And so 5-to-1 anisotropy explains the anisotropy, explains the data quite well here. And so that's consistent with these faults being filled with conductive seawater. So we published that in this paper in EPSL, and we also did, at the time we only had 1D modeling capabilities, and so we didn't really know what the potential of this data was, but we did 1D inversions of each of the EM responses from the CSEM receivers, and we were able to show that the crustal conductivity does increase in the bending fault region. But right after we published that paper, I finished writing a 2D inversion code, and so I gave that to Samer for his next PhD project, and this was the model that he came up with, and it really kind of blew us away because we had no idea that we could have this sort of level of resolution with EM data. So what went into this was about 32,000 data, so the amplitudes and the phase responses from all these receivers here as the transmitter toes by. We parameterized the model with about 30,000 model parameters, and we gave a relative error floor on the data of 2%, and we were able to fit to RMS1. So that's a really, really good fit to the data. To give you an idea of the computational power that this takes, we had to run this on a cluster with 320 processors, and it took about 16 hours. So you have to model Maxwell's equations in the full physics. There's no shortcuts with EM, and so it takes a lot of computational power, which is one of the reasons why we weren't able to really do this sort of project until the last few years or so, because we needed the computational power to do this. So let's go ahead and talk a little bit about the results. I'm going to divide it up into the outer rise and 4-arc sections just to make it easier to do it one step at a time. This is a close-up of the outer rise conductivity here, where the first thing I want to draw your attention to is this little red band here. This is about 400 or 500 meters of abyssal plain sediment. So these are just like muds and clays on the seafloor here, and they're very conductive. They're around 1 ohmmeter or so. And then beneath that, the yellows to greens and blues are where we're actually in the oceanic crust here. And so the first thing that you can see in this feature, though, are that we have these subvertical bands here of high conductivity going from the shallow crust down to the mid crust, and in some cases even into the lower crust. And so that was really astonishing to us. We didn't realize that we'd actually see these individual conductive zones associated with faults. And so you can trace out some of the fault scarps, like Samer's done here with these arrows, and you can see these conductive features match up with some of the fault scarps here, especially the ones with the big offsets on them. There's been some other work in this area, a lot of seismic work. There was a seismic refraction experiment by Van Dijk et al. Where they looked at P-wave velocities, and these little contours here are showing P-wave velocity anomalies in the uppermost mantle. So here's the MOHO right here with this gray line. And what they saw in their study were these low velocities concentrated right beneath the outer rise, and these were consistent with the outer rise mantle being serpentinized. So they concluded that the bending faults allowed fluids to percolate down and serpentinize the upper mantle. And so what we can conclude from our EM study is that there's these faults are porous zones that allow water to percolate down through the crust. And so it provides a mechanism for serpentinizing the mantle. Samer was able to use Archie's law to compute the porosity from the resistivity, right? So here's Archie's law again. For the pore fluid, we assumed that it was seawater, and then we assumed a temperature model as a function of depth. So we have a depth varying conductivity for the pore fluid. We measured the resistivity, and then we just assumed an exponent of 2 and solved this equation for porosity. And this is the porosity map that Samer got here, where in the shallow section it's on the order of 10 to 25% porosity, and then going down to maybe 1% porosity or so at the base of the crust. And so,
Why don't you see anything interesting in the mantle? Is it just?
I have a slide for you on that, just a few. So there's two things. I mean, the short answer is I'll show you in I'll show you in another slide. But one problem is that if these faults are really narrow, the conductivity is going to get smeared out. We start to lose resolution at depth. We still have sensitivity to the bulk conductivity, but the resolution is much lower at depth. But there's something else that I'll show you in just the next slide after this one. So looking at the crustal structure, Samer took all those porosities and then divided them up into different bands, or different distance bands from the trench axis. And so this is to try and map the evolution of porosity as the plate comes in and it starts getting bended and the fault fabric forms. And we can compare those predicted porosities with porosities measured from an ocean drilling compilation published by Gerard in 2003. And so that compilation was on a 24-million-year-old crust. And in the extrusives, there's a porosity of 10.4, in the dikes 3, and then in the gabbros 0.7. And 80 to 100 kilometers from the trench, the EM data predicts porosities of 12.2%, 2.7, and 0.7. So it's a pretty good agreement with this ODP compilation from the Cocos plate. And then as we get closer to the trench, you can see that the porosities start to increase. There's only a slight increase in the extrusives, but the extrusives are already fairly porous and fractured, and so you don't expect a lot of change there. But in the dikes and the gabbros, we can see that the porosity doubles and even more than double in the gabbros as you get close to the trench. So basically, you can say that there's about twice as much water being subducted, at least free water in the crust being subducted due to the bending fault. So that was sort of a first big result from the CSEM data. And then to answer the question about serpentinite conductivity, one of the targets of our project was to see if there were conductivity anomalies down here associated with serpentinites forming in the mantle. And when we did the experiment, there was only some really old data on serpentinite conductivity that was available, and there was about 3 orders of magnitude range in conductivity. The serpentinites could either be conductive or they could be resistive, and so we were kind of hoping they'd be the conductive serpentinites, but it ends up that all we saw was high resistivities here, and so that we kind of scratched our head for a while. And then since then, there's been some studies that have come out looking at the conductivity of serpentinites as a function of the amount of magnetite in the serpentinite. So when you first serpentinize a rock, you don't get a lot of magnetite forming, but if you have the right types of serpentinite reactions and they go on for long enough, then you can increase the magnetite fraction in the rock. And so there's this nice conductivity study by Kawano et al., where they looked at the electrical conductivity as a function of temperature and magnetite concentration, going from no magnetite here up to 100% magnetite up here. And so you get this huge range in conductivities. Most rocks, have much less than 25% magnetite, and unfortunately, 25% magnetite is really the sort of the percolation threshold where the conductivity really starts to jump up. And the way to interpret this is the magnetite, it's a lizardite. It looks like a little snake along the grain boundaries, and it's like a wire that will short circuit the otherwise resistive matrix of a serpentinite. And so you really need to have a certain critical fraction of magnetite to get that enhancement of conductivity. And so basically we can say that our results are not inconsistent with serpentinite, but they also don't really tell you anything, whether it's there or not. So, but it's not inconsistent with it. Okay, so now let's jump over to the forearc. So this is the image for the forearc zoomed in. We can see those sediments that we saw out on the abyssal plain coming in. The whole entire package of sediments is being subducted here. That's what this red feature is. It's going down the trench here. We also see the resistive crust going down beneath here. There's a thin veneer of sediments on the forearc slope here, but most of the interior of it is fairly resistive, which would imply that it has a low porosity. And so Samer looked at, the first thing he did was looked at the porosity and predicted fluid content along the plate boundary here, where this dashed line is shown. And so you can look at, when you take sediments and you subduct them down beneath the forearc, you have all the weight of the forearc pressing down on the sediments, and that compacts those sediments. And there's simple exponential decay models that describe how the porosity will be reduced. And it's simply a reduction as a function of the thickness of the overriding 4R crust and its density. And so these black and two black lines here are showing the predicted compaction that you would get along the Dave Lamont here for two different compaction models. And so you have porosities going from about 65–70% right at the trench seafloor, and as the material gets subducted further and further down, the porosity greatly decreases. And then Samer used our conductivity model to predict what the porosity is using Archie's law, as well as two different thermal models for what the temperature should be along the plate interface. And so that gives you these bounds here shown with the red and the blue lines. And so we can see there's pretty good agreement with the compaction model, at least in the deeper section here. We're getting lower porosities over here. So we know that there's a lot of water going down from this. Another thing that we could do is, instead of just computing the porosity here, we know that the EM inversion is slightly smearing out the structure because it's a diffusive process where, if there's any sharp boundaries in here, they're going to get smeared out. But we know that basically the bulk or the vertically integrated conductivity is probably more robustly estimated from the EM. And so what we did is we took the width of that red feature and basically integrated the porosity over it. And then we did that for both the compaction model as well as the porosity estimated from the EM image. And then we get these curves shown here, which are showing basically total water column in sort of a vertical direction. So it's water content per unit length. And so we can see that there's really good agreement now with the compaction models here. But then when we get about 20 to 25 kilometers from the trench, we have this anomalous zone of high water concentration. And that's associated with this weird feature here, this upper plate conductive zone that extends above the Dave Lamont. So this was, we expected to see sediments being subducted down, but we didn't expect to see this feature here. So it was really intriguing. And these conversions here or these estimates of water content show that there's a lot of water being stored in this feature. So that was a bit of a mystery, and we've been sort of wondering, what could this be? So there's one of the associated features here along the whole entire margin, in our profiles up here, is these dots here are showing the location of fluid seeps on the seafloor. And these have been imaged with side-scan sonar and bottom-looking deep-towed cameras. And this whole band of seeps here exists about 20 to 40 kilometers or so from the trench axis. They've looked deeper down and they don't see any seeps, whereas it's only the upper part of the forearc slope where they see these fluid seeps. And so that's kind of interesting because these the seeps, which are shown here with these little blue symbols, are located roughly above where we see this anomalous upper plate conductor that presumably is full of a lot of water. And so we've looked at a couple different hypotheses for what could explain this. One idea is simply that some of the sediments that are coming down here might have been scraped off and intruded or thrust up into the forearc crust. So that's one possible explanation. But if that's the case, you would expect there to be a big bulge on the seafloor, right? If you're going to thrust all these sediments onto the bottom of the forearc, then you'd expect there to be some sort of topographic signature of that. And there's maybe a little bit of a bump here in the at the top of the basement feature here, but it's too small. It's much smaller than the vertical extent of this feature. So another idea that's out there is perhaps this represents some sort of faulting or fracturing of the upper plate that's created a highly porous zone where fluids can build up. And so one of the things that we're really interested in is knowing what sorts of features or what sort of earthquake ruptures could create a porous zone like that. And so this is a slip model of the 1992 earthquake that occurred in this same region. So this is an earthquake offshore Nicaragua. It's a magnitude 7.6. It generated a small tsunami that killed some people in coastal Nicaragua. And this is the location of our EM profile here. And the red contours are showing the slip distribution that Lillian Ye and Thornley and Kanamori published a couple years ago. And so our profile is cutting right across this this location. And so one thing that was really interesting yesterday was Kimberly McCormick had this poster, and hopefully some of you saw it, where she was modeling the hydrologic response of an earthquake rupture in a subduction zone. So she basically had a model for slip, kind of like a model like this, and then she looked at what the pore pressures and the permeability response would be, both the static response as well as the transient response over time. So that got us thinking about an idea that maybe we could do one of her simulations for this particular rupture and see if the pore pressures are high enough to basically hydrofract the rock. So if the pore pressures exceed the lithostatic pressure, then you could potentially break the rock. So that's sort of a nice outcome of the poster session yesterday, is that we've got a new project going to look at that and see if that can explain our data. So that was the only CSEM data set that we've ever collected. We've been trying to get funding to collect more controlled source EM data for the past few years, and none of the proposals have been funded until last week. We just found out that this proposal that we submitted, that Samer took the lead on writing to do work off the Hikurangi margin in New Zealand. We just found out that this is going to be funded and the cruise will be in 2019. So I just want to advertise this as sort of this is what the next CSEM project will be. And so we kind of went ambitious, thinking that NSF would, if we ask for more than we want, because they'll cut us back. And so we proposed this grand experiment, and they just agreed to fund it. So we got lucky. So we have 3 CSEM profiles now instead of 1. And so we're going to look at the variations in slip, and plate locking and how that's related to fluid content along the margin. So there's these 3 different profiles of CSEM data. And the CSEM profiles are pretty cumbersome. The transmitter, we tow it at about, it's about 0.7 meters per second is the tow speed. So it takes a long time to tow each one of these lines. So we're only going to do 3. But once the CSEM's done, then we're going to take the fleet of EM receivers that are deployed along each line and redeploy them along these profiles here to get a 3-dimensional MT data set. And this will all be complementary to this huge array of 3D MT data that GNS, Science New Zealand, and other collaborators have been collecting over the last few years. Okay, so I want to go on. I know Terry would be deeply upset if I didn't include the mantle wedge and arc melting. So so I've got a bunch of slides here showing you other aspects of the subduction zone system that can be imaged with MT. And as you saw in Christy's talk, there's a lot of different processes that can generate fluids and melts here. In particular, we've got these dehydration reactions down here that release fluids into this hot region of the mantle wedge, where you could potentially generate melts, and those melts could travel up into the crust. We've also got dry melting or decompression melting that can occur due to small amounts of upwelling occurring here. And then in the shallower part of the system, we've got all these dehydration reactions that can release water. And so potentially we've got these free aqueous fluids that are going up into the crust. And so these are all potential targets that could be imaged with MT data. And unfortunately, these are too deep to image with CSEM. And we'd have the best resolution if we could do CSEM down to 80 kilometers depth, but it's just too deep to image. And also, you can't do CSEM on land, or at least you can, but it's really cumbersome because you unlike the ocean, you can't tow your transmitter, so it makes data acquisition really slow. Okay, so the first project I'm going to talk about is a survey that was done in Costa Rica. So this was just about 100 kilometers or 200 kilometers to the south of where our project was off Nicaragua. And this was done by the German group out of Guiamar, where they deployed a fleet of MT sensors across the oceanic part of the subduction zone as well as on land. So this was an amphibious project. And this is the conductivity model that they got here. And I'm just going to go zoom into their interpretation here. And so they see the resistive oceanic lithosphere, like what we saw off Nicaragua. They also see this conductive zone. They see it much deeper than we saw. So we saw it at around 50 to 60 kilometers depth. Theirs is much deeper, but they don't have as good a resolution as our survey because they only have 1 receiver out over the abyssal plain. So this could simply just be a resolution issue. They then have, where they do have more receivers is here, right close to the trench and then up into the arc. And they see, in our survey, we didn't see this conductive zone. They actually see a conductive zone at around 10, 20 kilometers depth here, where you go from resistive lithosphere to much more conductive. And they interpret this as being serpentinized mantle. So whether they actually can resolve this or not, it's maybe debatable. But in their case, they see something conductive there that they interpret it as serpentinite. So maybe there's magnetite off Nicoya Peninsula and no magnetite off Nicaragua. We got unlucky. And then here they're showing the plate subducting down as well as some of the earthquake hypocenters. And the next conductor that they see is this guy here, conductor D, right above the plate. And it's right where the plate goes from being aseismic to seismogenic. And so they think that this is associated with certain clay minerals in the crust dehydrating and releasing water into this reservoir in the overriding forearc. Deeper down, as the plate keeps subducting, they also see this enhanced conductivity zone down here around the E symbol, which they interpret as being fluids coming off the plate from serpentinites dehydrating and potentially generating either free fluids or free fluids and partial melt here. And then those fluids would rise up, and then they'd hit the continental moho, and they see this other conductor, the G conductor here, which they also associate it with fluids being stored in the crust. So that's a pretty nice sort of comprehensive look at where the fluids are coming into the system and then where they're coming out of the system over here. One of the other really exemplary results of MT on a continental subduction zone setting is this recent publication by McGarry et al. Looking at the CAFE MT profile. And this is actually the images from a recent review paper. So they switched it around. It's subducting to the left now instead of the right. But this is the map from the original paper where it was right subduction, the preferred subduction. And they had an array of both broadband and long period MT sensors out here, and there was a lot of receivers, a really dense profile, which is part of the reason why they got such a good result. And so this is the conductivity model here. The MT method is primarily sensitive to conductors. It's a lot harder to sense a resistor with MT data. So what they had to do here is actually impose the slab on their model. They actually put a break in the smoothness constraint of the inversion to help enhance where the slab was. So they basically assumed that the slab was here and that it was resistive. And so they're getting this model here where there's several different conductive zones. At around 40 kilometers depth, there's this conductive zone that's about 10 ohm meters or so. This is probably associated with some sort of dehydration reactions in, say, alteration minerals that are in the crust. And so that's releasing fluids up into the forearc mantle here. And then deeper down at around 80 kilometers or so, where you have the deep serpentinization reactions releasing these fluids, they can actually generate partial melts here. And so then you've got these partial melts and or aqueous fluids that are traveling up through the mantle wedge here, and then eventually they're placed into the crust, and eventually, at some point will lead to arc volcanism. And so you can take these sorts of conductivities, and we don't have a unique answer on what the melt fraction is or what the water content is. There's trade-offs and stuff, so we have to appeal to the petrology and other things like that to try and discriminate this, but this gives you an idea of the sorts of trade-offs between melt fraction and water content, where, and this is predicted at 1150 C. So, the resistivities that they're seeing here are around like 1 ohm meter or a few ohm meters, so basically where it's red here, so this whole region here is sort of compatible with the resistivities and their inversion. And so if you assume that there's, say, 2% melt, then you would say, okay, it's consistent with 7-8% water by weight in the melt. Conversely, if you had some petrologic indicators from, say, erupted samples here that you could use to constrain the water in the melting region, and you could say that there was, say, 4% water instead, then you might say, okay, there's 7% melt fraction. So those are the sorts of things that we can do with EM data. So I'm going to go on just a few more slides here really quickly. So there was a recent paper looking at the effect of chloride dehydration on conductivity, and that's shown in this nice plot here where they took chloride samples and started heating them and measured their conductivity. And so generally these hydrated clay minerals have very low conductivities. They're very resistive. But as they started heating these samples and they got to sort of the critical temperature, it started dehydrating and it released its fluids. And they noticed that there was this huge jump up in conductivity associated with fluids being released from the chlorides. And then as they heated the samples even longer, and this wasn't even a long experiment, I think it was 40 minutes to go from here all the way up to here, they noticed after the fluid release phase, they got another jump up in conductivity when magnetite started forming inside the crystal. And so they basically have said that some of these conductivity anomalies that we see in the mantle wedge might be explained simply by chloride dehydration and this formation of magnetite. And this is an image of some of the mineralogy if you're interested in looking at that in more detail. So their sort of interpretation is that you can have serpentinite and chlorites that go down with the slab, and then at some point these are going to be dewatered and lead to free fluids in the mantle. But if you have chloride up here in the mantle wedge And this is sort of roughly the temperature at which the chlorite is going to start dehydrating. So if the flow is coming in like this and you've got chlorite over here, as it comes back around and starts flowing down, it's going to enter this hot zone here, and it's going to release fluid as well as form magnetite, and so that could explain some of this conductivity. But we also know that you have to form melts here because that's how we get the arc volcanism. So there's probably some combination of all of these. Let's go on here just to show you a few more.
Time to finish up.
Yeah, I'll show you this last example then. This is an example of oceanic arc MT. This is done using low frequency MT sensors. So for the stuff that I showed you off Nicaragua, we could collect data to about 10 or 20 seconds period. These are long period sensors which can only collect data to about 1,000 seconds period. So they're imaging deeper structure and they don't have as much shallow sensitivity, but it is a nice big broad, it's a nice result because it's crossing an oceanic arc, which is, and it's pretty much the only oceanic arc where we have MT data. So this is what the conductivity model looks like. They see the resistive, thick Pacific ocean lithosphere over here. They had to put a break in the regularization to allow the slab to form. But they also see resistive lithosphere both beneath the arc and in the back arc, but there's really not much of a conductivity enhancement beneath the back arc spreading center here. There's a slight increase here, but it's not enough of an increase to really be much melt or free fluids here. But deeper down in the mantle wedge here, they do see this enhancement in conductivity, which they interpret as being consistent with at least a few percent partial melt or free aqueous fluids. So I think in order to leave time for questions, I'll stop there.
Questions from students and postdocs.
So in subduction zone situations, the water is considered to be always conductive because, as I remember from geophysics classes, water can be either conductive or very resistant.
Yeah, that's right. I mean, water, it really depends on the concentration of ions in the water to make it conductive. Pure fresh water is actually really, really resistive, like on the order of like 100,000 ohm meters or something. But most groundwater that we see is fairly conductive. It's at least 100 ohm meters, or at most 100 ohm meters, sometimes 10 ohm meters. And then when you're in the ocean and you've got all that salt around, then you have resistivities as low as 0.3 ohm meters. But there is a question with there's always an assumption when you interpret, some of these conductors in the mantle wedge as being, free fluids. It's assumed that there's some mechanism that delivers some sort of, dissolved ions in there that basically are salts that can enhance the conductivity. That's an implicit assumption. It can't be. You can't explain the conductivity if it was pure fresh water. There needs to be some ions in there that increase its conductivity.
I might have missed this, but can you explain what's going on with the trend with depth, how it's getting lower resistivity? Do you impose
right
lower
here?
Resistivity? Well, even at the bottom of the model.
Oh, down here, yeah. Yeah, so this is, conductivity, because temperature increases, in the mantle, basically the conductivity is always going to keep increasing as you go down deeper. So this sort of background profile here of going from resistive lithosphere to much more conductive mantle is what you would expect if you were just out in the middle of the ocean, just simply due to the temperature increase in the mantle. Yeah, so that's that. So you're going to see this no matter what, and so it's really the lateral variations that are coming in from the subduction structure. Yeah, I have another example where they go all the way down to the transition zone as well. That's later on. When we put the slides online, I'll make sure that those are included in there. But you can see sort of the same sort of trend here, where it gets actually quite conductive with depth.
I have a question. So as a seismologist, we always got a lot of criticisms on resolution issue about our seismic tomography.
Right.
So that's why we do some checkable tests, all kinds of synthetic tests. But here, I guess the inversion is more challenging, but is there any way to do similar tests to give a more?
Yeah, right. It's hard. The best technique that's available right now are Bayesian inversions. where you can basically sample a distribution of models that fit the data, but that's really only feasible for EM for 1D models. And so we have a bunch of projects where we're doing that for 1D. For these 2D and 3-dimensional models, the best that we can do right now are basically hypothesis tests, like resolution tests, where you put in a known structure, generate synthetic data, and then invert for that, and you see how sharp the feature is. It's sort of like a checkerboard test in that sense. And like, for example, in Sammer's papers on the Nicaragua controlled RCM data, we have a bunch of models where we put in these thin faults in the bending faults in the trench outer rise, and then we invert for those. We generate synthetic data and invert for those, and you can see how the resolution drops once the faults enter the mantle. So that's sort of the approach that we use right now, but maybe in 10 years from now we'll have 2D and 3D Bayesian inversions, which will give us a more reliable answer.
But overall, the system is overdetermined or underdetermined?
It's completely underdetermined. It's a really ill-posed problem. So we've got a finite set of noisy data, and so we heavily rely on regularization of the inverse problem in order to try and stabilize it. Yeah, I mean there's basically an infinite number of models that fit the data. So we choose the smoothest ones.
So without putting the slab stop in there, can you still see that there's a resistive?
Yeah, like in these sorts of inversions, you can see a little bit of a resistor in here, but it doesn't. It's not sharp at all. It tends to not have the right geometry. And it's one of the shortcomings of MT is that it's really not. It's only sensitive. It's most sensitive to where there's strong currents flowing in the ground, and the strong currents are flowing in the conductors. And so what's happening in the resistors tends to be harder to determine.
So how much of a difference does it make when you put the stop somewhere else?
That's a good question. They actually, I don't think they considered that in their paper. Like if you had the wrong slab, what happened? They didn't show that in their paper. It certainly would be an easy enough test to run. If you go to their paper, they did a whole suite of inversions where they had different types of constraints on the slab. And the location was always the same. But they looked at constraining the top of the slab, the bottom of the slab, or no constraints. And you can get a feel for how the results vary from that. Yep.
So, all right. Since I have the microphone, is there anyone who's working on joint inversion with both EM data and the seismic data?
Yeah, there's a lot of groups working on that for the industrial application of EM, so like joint controlled source EM and seismic inversion for looking at continental shelf structure. There are some groups working on that for MT, like Ninfa Bennington wrote a joint MT double difference tomography inversion code with sort of mixed results. At least all the data sets that she's tested it on so far haven't really been, it didn't really work so well. There's the problem with joint inversion. It's kind of a very broad phrase, right? How do you actually couple the inversions? And that's really where we're sort of waiting for a breakthrough to happen, because you can couple them through the regularization operator, or you could try to couple them through a mineral physics description where you have conductivity predicting porosity in mineralogy and seismology predicting porosity in mineralogy. And then, so there's different approaches to joint inversion. And so far there's no approach that's been, like really effective overall. There's approaches that work in some cases, but not others. Yeah, it's definitely an area of active research.
There's one more question down there.
So I just had more of a comment on the previous question. That McGarry paper and the supplemental material, they show their model where they don't impose the slab, so it gives you a nice qualitative view of what they can actually resolve with the method and the subduction zone.
Right, yeah, I mean, certainly there's a big difference. I mean, I don't have it in this talk, but there's quite a big difference. When they put the slab in here, it really enhanced this feature here. It's nowhere near as enhanced if you don't if they don't impose the slab on it. So, but both models fit the data. From a statistical point of view, the model without the slab imposed fits the data well, and the model with the slab fits the data well. So from that point of view, you can't say you prefer one or the other.
Your last slide.
Mm-hmm. Sorry.
In your study of the Central America, there's a low conductive layer when the plate
this one
bend towards the trench. But in this last slide, I don't see a low conductivity.
So these are, that was kind of why I warned you that these were low frequency MT results. So they're measuring fields at about, I think it was 500 or 1,000 seconds and lower frequency. So the skin depths that they're for those fields are on the order of like 50 kilometers or greater. They're really, really large skin depths. So they don't have as much sensitivity to the shallow structure as we had in offshore.
Shows 5 kilometer at least resolution.
Pardon?
The color.
Yeah, I mean, right. I mean, well, there's some sensitivity to shallow conductivity here, but it's not very well resolved. I mean, this shallow feature here could simply be because their starting model had a thin conductive layer in it, and it's hard to know. I mean, certainly where the data is really sensitive to is these features down here. Yeah.
So you teased us with these beautiful pictures of Akmak and Umnak, and
yeah.
So can you say just a little either preview of that or what you can do with kind of volcano scale?
Yeah, let me see if I can find my mouse again. Where did it go? So I have much more slides in here. Okay, so, whoops. I have one of those times where my mouse just disappears. Oh, here we go. Okay, so there's 2 projects. There was this project off Cascadia, which is this huge 3D project to look at, this was to image the fluids in the downgoing plate and how they're related to the ETS that's been observed here and the spatial variations in ETS. This is an ongoing project. We presented some results at AGU last year where they're almost publication ready, but there's still some issues with the modeling code. Like, for example, it can't actually handle the marine data very well. So we've been holding up trying to publish that until we fix the modeling code so that it works better. And yeah, but I didn't want to show the results here because they're not published yet, but we do see some really interesting conductivity anomalies right beneath the coastline. And these are conductivity anomalies probably associated with fluids right along the plate interface there. And then they show some systematic variations along the strike here. Yeah, the volcanoes, yeah, yeah, sorry. Yeah, so, okay, so I remember why I was gonna show you. So there's also the IMUSH project here. So these are the MOCA stations here for looking at ETS, and then there's the IMUSH project here, which is a few hundred MT stations. And these are targeting Mount St. Helens and Mount Adams. And I actually don't know what the results are yet. I don't know if they've actually got results out of this. They were still collecting the data last year. And it's a big data set. And it's going to be a challenge for them to model this in 3D. I mean, they'll be able to do it, but it'll take a while.
Who's doing that?
It's Adam Schultz is leading that. So, yeah, and then we also have a project looking at Akmak volcano in the Aleutian Islands, and that we've done some 2D modeling, but the data is really 3D, so we're sort of waiting to get the 3D code up and running on that. So, but hopefully that'll happen soon.
So we're still being teased.
Yeah.
More on Saturday.
Yeah, right. So for the shallow volcanics, yeah, Matt's going to present some really nice results from South America.
Yes, some of your models show like 4 or 5% melt in the mantle.
Yeah.
But a lot of people think that's impossible because of the high permeability that you should have for porous flow, and also I think some U-series equilibria if you interpret it, in the conventional way. So,
right.
So, do you have any comments on that, or should people take those numbers seriously? Or?
Well, I mean, it's one of these things, right? I mean, Christy's talk kind of was a little bit cautionary on that, where right, so you have to, so we have conductivity, right? And what affects conductivity? Well, there's the melt fraction, and then there's the melt composition, and then there's the temperature, and there's what the solid matrix composition is as well. And and Christy showed in her talk that the whole solidus curves and all that, they vary all over the place. So you have to pick somebody's model that you're using and things like this. And so it's the same thing when we're looking at some of the studies for how conductive hydrous olivine is, how conductive is a hydrous melt. There's a whole range of results that are out there, and they might be good results for the conditions that the laboratory measurement was made in, but they might not be applicable to this particular subduction zone or this particular mantle, oxygen fugacity and things like that. So yeah, I mean, it's basically we do the best that we can with the available data, but take it all with a grain of salt.
I think there's one over there, and then we'll have to finish up maybe one more.
I was thinking back to Jessica's talk yesterday and remembering a day when people used to talk about the deformation processes in olivine maybe combined with hydration would actually produce an electrical anisotropy that was very much correlated with seismic anisotropy. Is that still something that we think may be true, and is it something we should be looking for?
Yeah, there's an ongoing story about that, and I mean, I can give you a little teaser on that. That the hydrated olivine does have a small anisotropy, in it, and so you could expect some sort of shear or flow line olivine to give you a small amount of anisotropy. But there's been some recent studies, and it's not yet published, but Anne Pomier's done some studies, laboratory work, looking at sheared, dry olivine, or actually it was a sheared, it was sheared olivine, and basically she's shown just the fabric of shearing it. If you get like a shear strain of like 7 or 8, you can end up generating a really significant anisotropy at mantle temperatures. And nobody's made those measurements before, and so she's having a bit of trouble getting it published. But if that gets published, that's going to be a really interesting thing for us to look at with EM data sets. And I think some of the controlled source EM data sets do. We didn't have time to talk about it today, but we have controlled source EM data from the Pacific plate that shows an anisotropy in the upper mantle that's consistent with her laboratory results. So we're pretty excited about that. But this is all ongoing stuff, and the story could change.
I'm interested in this layer that's interpreted to be melt rich under the slab. If you enter the subduction zone, do I read the slide right that once this layer, once you enter the subduction zone, actually this layer kind of gets weaker and weaker. Is that still the?
Yeah, Sammer did some resolution tests where we looked to see, if you put a conductor in here, would we be sensitive to it? And yeah, the data is sensitive to that. So we can say that this, these stations here are constraining that there's not a strong conductor going down with the plate. So, if this is melt, then there's some sort of mechanism, buoyancy or something that's keeping it here rather than allowing it to go with the pores.
What happened to the melt? I guess that's the.
Pardon?
What happened to the melt once it's subducted?
Our model would suggest that it's not being subducted. It's simply staying there. It's staying up here. It has to move then. So if the melt is being transported down here, then something allows it to flow back up and collect here, which seems to imply that you have to create new porosity to allow that to happen. So there's it's not a full explanation, but it seems one it's not a complete explanation, but one idea is just simply that the melt just buoyantly stays there at the base of the lithosphere. It's hot enough here that you can have porosity, whereas up in the lithosphere it's too cold to to melt the rock, and so it's going to be relatively impermeable. Magnetometer, it measures the time varying part of the magnetic field, so it's completely insensitive to the static magnetic field. And so that's sort of an overview of what the geophysical approach looks like. Now I'm going to talk about resistivity and why you should care about measuring it. So electrical resistivity, we tend to denote it with the Greek symbol rho. It's an intrinsic property of a material. The units are ohm meters. Sometimes we'll write it as omega meters. And it's simply, you can determine resistivity of a sample simply by putting it in a series circuit and measuring its resistance. So you could use an ohm meter, although in practice we use much fancier approaches than that. You measure the resistance of the sample, and then you simply scale it by the area, the cross-sectional area, and the length, and that gives you the resistivity. So this is resistivity. It's just like density or seismic velocity. There's an intrinsic value. Every material has an intrinsic resistivity. And then conversely, if you actually wanted to know the resistance of a sample, you could take its resistivity and then multiply it by the length, divide by the area, and that would give you the resistance of a sample. Okay, and then in electromagnetics, we tend to flip back and forth between talking about resistivity and talking about conductivity, and they're basically the same thing. One is the inverse of the other. So 1 over rho is the conductivity, and we tend to write conductivity as the symbol sigma. And you'll see me switch back and forth between those. So resistivity has units ohm meters, and conductivity has units of Siemens per meter. So this is a chart to sort of impress you with the huge dynamic range of resistivities that we could expect to see in the Earth for a whole range of properties. Here we're spanning about 19 orders of magnitude, although in practice what we tend to see in our experiments is only about 3 or 4 orders of magnitude. But there's a whole variety. Sort of the primary variable that affects the bulk conductivity of rock is its porosity and fluid content, and then the secondary effect would be temperature. Let's see here. Okay, so another thing, a lot of EM methods have been, the technology has been advanced a lot in the last decade or two due to a significant amount of investment from the oil and gas industry. And they were interested in this resistivity contrast here, where oil or gas in the seafloor tends to be fairly resistive, maybe 100 to 1,000 ohm meters. And an oil reservoir on the continental shelf will be resistive, and it'll sit in these conductive wet sandstones. And so there's this nice resistivity contrast. And in the early days, the late 1990s, early 2000s, when this technology was being commercialized, there were people in the oil and gas industry that were saying that you could use resistivity as a direct hydrocarbon indicator. And we were like, no, no, no. If you go out and you measure something and it's 100 ohm meters or 1,000 ohm meters, it could be anything on here, as well as all the other things that aren't shown on here. So, for example, you could see a resistor, and then if you work in an oil company, you could say, I want to go drill that, and your company will spend $40 million drilling a deep water well, and then maybe if you didn't know what the geology was, maybe the resistor was a basalt, a sill, or maybe it was like a limestone or carbonate or an evaporite deposit. So, resistivity is not a unique indicator of rock type. We need to integrate with geology and other geochemistry and other methods in order to build up an understanding of what the resistivity is telling us. Okay, so that was resistivity of rocks and minerals. There are models for if we have two-phase or three-phase systems to predict what the bulk conductivity would be. And so we can use various mixing laws. The Hash and Strickman bounds are nice because there's seismic equivalence to these. And they're basically theoretical bounds for a variety of different materials here. Let's see, what can I draw your attention to first? So like basalts, lavas, and igneous rocks, these tend to be fairly resistive. So this is a logarithmic scale here as well. So this would be 1,000 ohm meters here. Something like partial melt, so all the stuff that Christy was talking about in her talk, those tend to be fairly conductive. So there's usually about a factor of 1,000 contrast or more between a pure partial melt and then a solid igneous rock or basalt. And then all these things have quite a range of conductivities. Like any given material has quite a range of conductivity that it can be, and this depends both on temperature as well as the porosity and fluid content. So for example, a sandstone here, if it's very dry, can have a very high resistivity, over 1 million or so. Whereas if you fill the pores of that sandstone, say it's like a 20% or 30% porosity sandstone, its resistivity is going to be closer to 1. So it's very sensitive. EM methods measuring resistivity were very sensitive to the porosity and fluid contents of rocks, whether they're filled with seawater, which tends to be conductive, or melt. And then some sort of end members here. Air is very resistive, about 10 to the 13 or so. And then like graphite and some ore grade minerals will be very, very conductive. So here we have 10 to the minus 5. And if you were to look at the types of metals that are used in wires like copper, gold, and silver, those are actually a few orders of magnitude over to the left here. They're very conductive. So resistivity spans many orders of magnitude. Yeah, Sean? What's the pressure here? This is just sort of at ambient pressure. I'll talk about that in a second here. Ends up the pressure dependence of most of these rocks and minerals. The pressure dependence of conductivity is fairly low. It's very weak, especially compared to the effect of porosity and fluid content and temperature. Those are much bigger effects. But okay, thanks everybody for coming back. My name's Kerry, and I'm going to talk about electromagnetic imaging of subduction zones. And I'm really happy to be giving this presentation after Christy's really good talk on magmatism and melting, because one of the key uses of EM methods in a subduction zone setting are to image melts and free fluids coming off the slab. And so I'll talk quite a bit about that. So it was nice to have, now that you've seen Christy's lecture, some of the things when I show solid eye and things like that, it'll be a little bit easier to digest. Also want to acknowledge Samer, who's over there, who contributed some slides to this, as well as Stephen Constable. So this is being sort of a tutorial lecture. I broadly divided up the talk into 3 different pieces. Sort of the why do we care, why should you care about electromagnetic methods, and that's because they measure electrical resistivity, which is a physical property of geologic materials. Then I'm going to talk about the actual geophysical methods that we use to measure electrical resistivity in the Earth. And then I'm going to give a whole suite of subduction zone imaging examples that will go from looking at the shallow crust at the trench, looking at the forearc, and then looking at sort of crustal and arc magmatism settings. Okay, so what are electromagnetic methods? Well, they're methods that measure time-varying electromagnetic fields in the Earth. So they're not static methods like DC resistivity. They're actually time-varying electromagnetic fields. And we measure the response of the Earth to those time-varying electromagnetic fields. In the same way that, like, if you go out and do a seismic experiment, you're measuring the seismic response of the Earth to whatever the seismic source is, whether it's an earthquake or an air gun. So it works like this. We have sources and then receivers, and generally the more sources you have and the more receivers you have, the more resolution you have. There's several different types of sources that we can use for EM methods. The easiest one is a natural source field. They're just ambient plane wave electromagnetic fields associated with something called the magnetotelluric method. And these are low frequency electromagnetic fields that are generated in Earth's ionosphere, and they diffuse down into the Earth and induce secondary electric and magnetic fields. And we can do this for low frequency deep soundings in the crust and the mantle. If we want to image shallower structure and in higher resolution, then we need to create our own artificial sources. And the two primary source types that you can use are a grounded wire, where you inject a current into the ground or into the ocean, or you can use a loop source like this, where you have a loop of wire and you pulse a current through that, and that generates an electromagnetic field that diffuses out from that source. Primarily for the subduction zone imaging, where we're trying to image things on the scales of kilometers to tens or hundreds of kilometers deep, we're going to look at the MT method and then these grounded wire sources. These loop sources tend to be really good for shallow imaging in the upper 100 meters or so, and in fact there's been a lot of use of these loop sources and receivers for airborne electromagnetics, and some of you may be familiar with like helicopter EM surveys that are really high resolution, but unfortunately they don't sense deep enough for us to use for subduction zone imaging, unless you were trying to image, say, shallow magma on an arc volcano. And then the receivers that we use are very similar. We can have either a grounded wire, which would measure the electric field, or we can have an induction coil, which is very sensitive